Hi, everyone. I am Sharon London. I am the Director of Philanthropy at Washington's National Park Fund, and it is my pleasure to moderate today's virtual field trip to Mount Rainier National Park with our very special guest, Dr. Claire Todd. First, a little bit about Washington's National Park Fund. We've been growing strong for many years. We have a 23-person board of directors who work really hard to help the parks, as well as 7 highly competent staff members. We have strong engagement with the parks. We work really closely. And each year, the superintendents provide their priority projects that we set out to fund. So in our vision is to see that our parks are strong and vibrant, youthful, and everlasting. Before we start, a few housekeeping items. This is a 45-minute virtual field trip with a 30-minute presentation from our speaker, Dr. Claire Todd, with questions and answers at the end. Please enter your questions in the Q&A box or in the chat box, because Claire is very willing to be interactive with you as she does her talk. So feel free to just type questions in the chat. And we have closed captioning at the bottom. So feel free to either keep it on and you can adjust the font, or turn it off if you prefer. And afterwards, we welcome your feedback, as we'd love to make these field trips as accessible as possible. And we want to know what you like and didn't like and what we could be doing more of. So are your backpacks ready? Do you have your hiking boots on for our trip? Are you ready to board the virtual bus and travel to Mount Rainier National Park? So now about our speaker, Dr. Claire Todd. Claire is a professor of geosciences who studies glacier and ice sheet response to climate change on Mount Rainier and in Antarctica. Since 2008, she studied Mount Rainier glaciers with undergraduate students at Pacific Lutheran University. This fall, she begins a new position in geological sciences at Cal State San Bernardino, and she will continue her summer research season on Mount Rainier in the coming years, which we're very excited about. And on a personal note, I first met Claire because Claire is actually a monthly donor to Washington's National Park Fund. And not only did Claire donate, but she offered to lead a virtual field trip, which we're going to experience today. And then I asked Claire, hey, would you like to lead a guided hike to Emmons Glacier as part of our spring auction this year? And lucky for us, Claire said yes. And I had the pleasure to go on this hike with Claire and the winning bidders earlier this month, which is why you see my background is very similar to what Claire is going to show. I didn't know that visiting the terminus of Emmons Glacier would be on my bucket list, but let me tell you, it is. It was awe-inspiring, and Claire's enthusiasm and excitement about glaciers is contagious, and I am certain you will enjoy this presentation. I'm also pretty sure that all of Claire's past, present, and future students have a greater love of geology because of Claire. So Claire, thank you for all you do, and please take it away.
Wonderful. Thank you, Sharon. We did have a great time on the mountain. We had a wonderful time together. And so I'm excited to explore even more some of the things that I see when I work on Mount Rainier's glaciers. And today we're going to be focusing on 2 phenomena. We're going to be talking about debris-covered glaciers, which you can see in the lower part of this picture of Emmons Glacier here. And then we're also going to be talking about debris flows in the second half of the talk. So it's my great pleasure to take you on a virtual field trip. I'm really excited to show you 2 of my favorite places in the park. So without further ado, let's jump right in. So first of all, it's important for me to acknowledge that so much of my work and the work of other scientists happens in community. We require funding, we require other scientists. There's a great geology team at the National Park Service, Scott Beeson, Robbie Just, and Taylor Kenyon. I partner with Michelle Kutnick at the University of Washington. And the National Park Service has done a great job supporting my work at Mount Rainier. So as a lot of people that I'd like to just sort of acknowledge, including Tara Chestnut and Kelly Babcock. Tara Chestnut gave a great virtual field trip earlier in the sequence, so I encourage you to look up her talk. And also, I have had the good fortune of working with so many hardworking students from PLU over the last 10 plus years. You can see some of them pictured in the bottom here. So a lot of the work and ideas that you see today come from my collaborations with them. And I'll also at times may see a parenthetical or a name and a year in small font at the bottom of the slide. And that's just acknowledging the work of other scientists. So this is just, my piece is just one tiny piece of the puzzle, and it comes together through lots and lots of collaboration. So I wanted to acknowledge that. So we're going to travel to 2 locations today. We have the good fortune of being able to just zip over the mountain quite quickly in a virtual talk, of course. And so I'm going to begin looking at Emmons Glacier here in the northeastern corner of the mountain. And then we'll travel to think about South Tahoma Glacier in the southwestern corner of the mountain. And we're going to start off looking at debris-covered glaciers with Emmons Glacier as an example. So to get to Emmons Glacier, we begin our trip today from the parking lot at White River Campground, also known as the Glacier Basin Trailhead. And you can see a team of my fearless students here getting ready for a day's hike, which is what we're about to do. You follow the Glacier Basin Trail up about a mile, a lovely tree-lined trail. It climbs gradually. Along the trail, you can see outcrops of some of the lava flows that shape Mount Rainier and even some other types of rock. And it's those waterfalls coming down. It's a lovely, lovely hike. And about a mile in, you make a left turn to what's called the Emmons Moraine Trail. So there's a lot going on in this picture. Let me walk you through it. So here's our icon, Mount Rainier. That's the summit of Mount Rainier that you are looking at. And Emmons Glacier descends down from the summit of Mount Rainier. One of the state's other tallest peaks, it's either the 4th or the 5th tallest peak, is Little Tahoma. This will be a landmark we'll use throughout the talk. And just below Little Tahoma is Frying Pan Glacier, a different type of glacier from Emmons. It does not have debris on its surface. It's at a much higher elevation with fewer surrounding rock walls. So in the foreground, you are looking at Emmons Moraine. We'll talk about what a moraine is in a minute, but Emmons Moraine is the namesake of the Emmons Moraine Trail, which we will take a left on, and we'll cross over this bridge right here, barely visible, which crosses the Interfork. And the Interfork is a meltwater stream that comes from the Interglacier. If there are any climbers in the talk audience today, many climbers begin their journey up Interglacier to get to Camp Sherman. And so that is a destination known by climbers. So we'll cross the Interfork on this bridge, and then we're going to travel up this trail that climbs the side of Emmons Moraine. Notice here that the Interfork is actually eroding the Emmons Moraine pretty aggressively. So you can see all of this tree debris and lots of rocks that have been deposited into the river channel as the river continues to erode into the side of the moraine. Let's take a closer look. So what is a moraine? One of the things that I like to do is just to acknowledge that we can all be geologists, or we can all be scientists of different types, because we can observe things. It's one of the first things that we do as scientists. So the Emmons Moraine Trail takes us up this zigzagging route up to the top of the crest of the moraine. And so thanks to the Interfork, that river you just saw, we actually get a view of the inside of the moraine, because so much of it has washed or has been fallen down into the river channel. So when we make observations about this image, we see large rocks, small rocks. We see everything's unsorted. When a geologist says things are unsorted, it just means there's no sorting by size. Small rocks and large rocks are coexisting. And these rocks all look pretty battered. So their edges are bashed around a little bit, and they have been deposited by a glacier. So let's think a little bit more about that. A moraine is a deposit of glacial debris, and debris is a word that some geologists use to describe rocks and sediment. And glacial debris is simply rocks and sediment that are transported by a glacier. And moraines are often linear features that mark a past glacial boundary. So you can see our fearless team here has made it to the crest of Emmons Moraine, as we have. And Emmons Moraine is a lateral moraine, which is to say it forms a side boundary, a former side boundary of where Emmons Glacier used to be. So as we go a little bit farther here, we're now looking down toward Emmons Glacier from the top of that lateral moraine. And you can see a different team of students, but a team of students descending the inside of the moraine toward the glacier. And again, look at this unsorted debris, lots of different sizes. While water sorts sediment by size, if you took a bucket of rocks full of lots of different sizes and threw it in your bathtub, the heavy ones would fall out first and the fine grain material would settle down more slowly. Glaciers can't sort rocks, so they just leave behind a mess of all different sizes. And so we can use moraines of this glacial debris to tell us where glaciers used to be. And in fact, you can see there's a lateral moraine on this side of Emmons Glacier, but there's also one on the far side of Emmons Glacier, a little harder to see, maybe a third or a quarter of the way up that hill slope. And they're actually a pair, showing us a past elevation and extent of the glacier. So my question for you, we have a poll now, Casey. When did Emmons Glacier last reach this lateral moraine? When did Emmons Glacier last reach this lateral moraine? And glacial geologists you can find moraines all over the world, and glacial geologists map those and can actually calculate rates of glacier retreat. They can calculate how much ice volume has been lost. So we're seeing a range of results coming in now. Hopefully you can see them on your screen. And so those of you who indicated 19th century, the majority or close to a majority of 48%, you are correct. So right around the late 19th century, turn of the 20th into the 20th century is when Emmons Glacier last filled this space. Now, it turns out this moraine is actually a complicated feature. It has what's called a terminal moraine in sort of behind the photographer in this photo, farther down valley. So it has actually occupied this space multiple times, even going as far back as the 15th century. But the last time it retreated from an extent approximated by this lateral moraine is in the late 19th century. So you can see then this space would have been totally filled by ice. So that's our first glacial geologic exercise. So let's orient ourselves one more time and think about the glacier itself. So we have our landmarks that I labeled earlier, labeled once again for you. And when we think about a glacier, we think about its sort of lower area and upper area. We're going to focus on the lower area for a second because it's one of our destinations. So in this image, you can see what I've been calling the debris cover. It's simply rocks and sediment covering the lower part of the glacier. You can see the glacial terminus. It looks very sedimenty, it looks very dirty, but that is actually an exposed ice face. And then you can see the meltwater stream, the beginning of the White River, those of you in the region might be familiar with, emerging from its terminus out here in the foreground. And then the upper part of the glacier, we've changed views now, but I've left our labels there to orient you. The upper part of the glacier we call the accumulation area. So that's where the glacier gains snow and has snow that sticks around for more than 1 year. It has a positive mass balance for that year. The ablation area, where we find the debris cover, is the lower part of the glacier where the glacier experiences a net loss of mass per year. And so this can be a little deceptive. So for those of you who visit the park even in the spring months, perhaps, you may find a park that's totally under snow. And so the snow is, while the ablation area receives snow during the winter, it melts away completely in the summer. So even snow in the lower part of the glacier is gone and does not actually add mass to the glacier in the long run. Great question about how tall the terminus ice face is. That's a great question in the chat. I haven't measured it directly. It's actually dangerous to get very close to it, but I would guess, this is just a guess, that I would guess maybe 100 to 200 feet. That's tough. I'm going to come back to that question and let myself think about it a little bit longer, but great question, Michael. Thank you. So Emmons Glacier has the largest area of any glacier on Mount Rainier or even in the lower 48. So Casey, we have another poll. How much area does Emmons Glacier cover? Largest glacier on Mount Rainier, and even in the lower 48. Alaska has bigger glaciers than we do down here, but in terms of the lower 48, Mount Rainier Emmons Glacier is the winner. How much area does it take to be the biggest glacier? All right, we've got some answers coming in. Yep, absolutely, 4 square miles. So we've got an audience that's really in tune to this glacier. Well done. Yeah, it's actually 4.25 square miles of ice and rocks, and that would include both the accumulation area and the ablation area. And over a quarter of this area is covered by debris. So we still have some areas of negative mass loss above the debris cover. So the ablation area is actually bigger than this debris covered area, but let's take a closer look at this debris cover. So here are a team of students who have climbed onto the debris cover with me. And you can see, again, we see these evidence of glacial debris, unsorted debris of all sizes, including we find fine-grained silt and clay. You can actually see some of the ice surface underneath the rocks here. So we have very fine silt and clay in places. We have very large boulders in places. For those of you who are still orienting to the images, here's the upper portion of that lateral moraine that we've been talking about in earlier slides. So we have lots of unsorted debris of all sizes, and that debris cover can be very thick. So greater than 1 meter, which I'm showing over here on the left side, or it can be very thin. So in places, it can be, you can see exposed ice, 0 centimeters, or it can be, up to 10 centimeters in areas even close to exposed ice. So we see a wide range of both sizes of debris, but also thicknesses of debris. And this actually matters in terms of the glacier's future. So when we see areas of ice exposed in places, envision these rocks right next to the ice, absorbing solar energy all day. If it's a thin cover of debris, we can actually see accelerated ice melt. The rocks get hot and melt the ice. So we see thin debris, and in some places that can actually make melting happen more quickly because the rocks are absorbing that heat and increasing the temperature in that location. However, in areas of thicker debris, we can see places where that thick debris is actually insulating the ice from solar radiation. Some great questions coming here through the chat. The history of that huge rock, it would be tough for me to say with certainty, but I do know something about how rocks arrive at the glacier surface. So there's lots of different processes. One is that in the middle of the glacier, you can see these bedrock fins, rocks of fins of bedrock sticking up through the glacier that are telling us about all the bedrock underneath it. So the glacier is really good at scouring the sides of Mount Rainier, and it delivers rock to its surface farther down the glacier. So the glacier is actually a conveyor belt. It's eroding rocks in different places along its flow, and then those rocks eventually end up in the debris cover or out in front of the glacier. So that rock could be an erratic, which is a word to describe a rock that's been transported far from its source by a glacier. It could be an erratic. The other way, though, that many rocks have traveled to Emmons Glacier is through rockfall. So in 1963, Little Tahoma is here. In 1963, Little Tahoma had a giant steam explosion event that filled the valley, starting about halfway down the glacier, filled the valley with sediment, a huge rockfall event. There's a great 1964 publication from the US Geological Survey that has great images of this. But they're basically another way, and that's just one event, a big event. But that's another way that rocks can arrive at the surface, is to just rockfall. In that case, they wouldn't be an erratic delivered by a glacier. These are great questions. So, but generally speaking, either rockfall or glacial transport is one way that we can get rocks arriving in these locations in the way that we see them in this image. So the future of Emmons Glacier, one of the reasons that my students and I are studying the debris cover is the future shape of Emmons Glacier, the rate of melting of Emmons Glacier is determined by its debris cover. So it's determined by other things, of course, by the accumulation of snow at the summit, by temperatures that cause melting, but it is also a function of this debris cover and where we find thin debris versus thick debris and how that changes in time. So that's a kind of a key take home point for us as we go to our next location. And I'm looking at the time and want to make sure that we have a chance to visit the other side of the mountain, but I'm really appreciating the comments in the texts, in the chat. So thank you for that. Lots of people who have some great experiences with this glacier. So let's go to the next stop. We're effectively flying over the summit of the mountain here, and we are going to go visit South Tahoma Glacier. So when we're on our, sometimes when we are in our non-mountain lives, we often read about Mount Rainier in the paper, and it's often about things where there's either been a geologic hazard or some kind of incident. So for those of you who read about Mount Rainier in the local papers, for example, in August 2015, you would have found a couple of articles about a glacial outburst from Mount Rainier. So I'm including two images and from those articles about these glacial outbursts. And so you can see, it's very hard to, but there's a dotted line in this right-hand image that shows the Wonderland Trail. And the Wonderland Trail crosses Tahoma Creek on this suspension bridge shown in the photo on the left. So let's think a little bit more about this area and location. So if you wanted to see South Tahoma Glacier on foot, not virtually, you could do so from the Couts Creek Trail or the Wonderland Trail. And South Tahoma Glacier, much different from Emmons Glacier. It rests in this rocky basin here, beginning sort of at this location where you see the snow and ice peeking out above the clouds. So again, different side of the mountain, looks very different. And I had the opportunity on August 13th to actually witness the debris flows. I was hiking the Wonderland Trail with my sister. And so if you had traveled from this trail, you actually can't see the Wonderland exactly in this trail, but it passes in front of that patrol cabin. So you would keep walking along the Wonderland Trail and you would descend the trail toward that Tahoma Creek suspension bridge shown in the news article. And so I was doing so with my sister. Why I took this picture, I don't know, because it was a very normal sound. All we heard was river noise. And I guess as a geologist, a picture through the trees of these rocks really appealed to me. So, but I show it now because in the what we learned later about this location is actually visible in this photo. So we've descended toward the suspension bridge that crosses Tahoma Creek, and Tahoma Creek is supplied by South Tahoma Glacier. Notice the time up here, 10:29 a.m. And when I went back to my photos later, I started to notice some signs that a debris flow had occurred. So here's Tahoma Creek here. Again, I realize it's a little bit hard to see, but Tahoma Creek is this width here at this point in time. But there's a high water mark, a recent muddy high water mark. And this large boulder, which you can't see very well in this image, we are going to use as a visual cue in the next one. So my sister and I are talking along the trail. We're getting ready to sort of go to the suspension bridge. And as we get to the suspension bridge, another debris flow happens. How do we know? The ground starts shaking in a terrifying fashion. It unmistakable. There is a loud roar like a freight train or like a giant truck or motorized vehicle approaching. My sister will tell you that I started jumping up and down and yelling, which she thought was in fear, but actually was in excitement. Because as a geologist, this is basically like winning the lottery. So what I'd like you to notice now is the channel is wider and that boulder has disappeared. And I'm using this arrow to show the front of the debris flow. So it's just 2 minutes later, and there's a loud roar in the background. The front of this debris flow passes the suspension bridge. This boulder is beginning to emerge. The roar is quieter. Now we can fully see this, or almost fully see this boulder, and the debris flow has passed farther down the valley. You can think of it as a mixture of sort of wet cement, but it has boulders in it, and it's moving a few meters per second. That is my visual estimation. That's not an actual measurement. And we are safe only because we are high up near the suspension bridge. Had we been in the channel, it would not be like winning a lottery. It would be a life-threatening experience. As we keep going, we see the boulder fully now, which I estimate to be about 1.5 meters in height. And we see this flood of debris and this cloud of dust it's creating advancing down the valley. I think the event is over. It is not. I just zoomed in here to show you the boulder and the front of the debris flow, which looks like that wet cement mixture. And then we see hear another roar again a minute later. And in the next slides, you'll see a similar sort of phenomenon where I've shown you the boulder. The boulder disappears again, about 1.5 meters in height, and another surge of debris goes down the valley. So what's happening here? This is actually an event that has been quite well studied by Scott Beeson, the National Park Service geologist at Mount Rainier. And he wrote a great article published this year describing the event and other history of debris flows in this area. And so up to 12 individual flows, 4 registered on seismometers in the area. This is all just on August 13th, 2015. Triggered by an outburst flood from South Tahoma Glacier, the terminus of which is perched up here behind this knob. And it occurred after an apparent obstruction in flow. So basically that the meltwater flow had been blocked. As we think about kind of what we can do here, let's go up to the glacier itself. So we're looking at South Tahoma Glacier up close. This is an image taken by a time-lapse camera that I'm going to show you a picture of in just a minute. So again, same concepts apply. And what we're trying to figure out is how debris flows occur here. So there's there's a poll question up on the slide. How many South Tahoma Glacier debris flows have been documented since 1967? So I want you to guess, how frequent do you think these events are? How many debris flows have been documented since 1967? We'll get back to the slide in a minute and just orient ourselves to the glacier itself. But we saw one example of a debris flow. How many have happened since 1967? And again, we've got an audience that's on top of things here. So Scott Beeson, in his article, explains that at least 33 debris flows have been documented from South Tahoma Glacier since 1967, and that this is likely an underestimate because of incomplete record keeping during some of that time. So these are not infrequent, certainly from a geologic perspective, although perhaps in a human lifetime perspective or time spent on the mountain anyway. And notice that this is a much smaller glacier. Although there's no scale on this image, I'll tell you that South Tahoma Glacier has an area of about 3/4 square miles, so much smaller than Emmons Glacier. And the terminus of the glacier where water would be released is sort of hard to pick out because of the bedrock in this area. But there is the glacier terminus here. What we're doing about this is we've installed a time-lapse camera. So there's yours truly behind the time-lapse camera installation. It's not transmitting images that we can pick up from our offices or homes, unfortunately. We pull the images down at the end of the season. But this camera is perched at the base of Pyramid Peak, which is not visible in this photo, but on a bedrock bench just across the valley from the glacier terminus. And so what we're hoping to learn is more about what causes these debris flows. So we already know some about this process. We know that water can be stored beneath the glacier because of irregularities in the bedrock, or because something is blocking meltwater from being released. So perhaps a piece of ice falls and blocks the water from being released, either in the front of the glacier or inside the glacier, or even a landslide of some of this loose glacial debris might create enough blockage such that an outburst of a bigger volume could be released. And these we know so far are triggered by periods of hot weather or storm events. but we like to capture what happens in the event of some of these established triggering factors. So our goal is that this ongoing monitoring will help us better understand and actually document the onset of these events. Okay, so that's what I have for you. I'm grateful that you showed up today, and we're eager to learn more about Mount Rainier's glaciers. You got them from a glacial geologist's point of view. Of course, there are many other people studying glaciers on Mount Rainier that know about them from lots of different perspectives. I wanted to share this photo. Sharon mentioned that we had a hike, a Washington's National Park Fund hike earlier this month, actually. And we had a wonderful time, and I hope I have an opportunity to take other Washington National Park Fund supporters to glacially interesting locations on Mount Rainier. And in the background, you can see the terminus up close here, and I'm still thinking about that, that estimate of the how tall it is, but you can see the terminus in the background here. I'm happy to take any questions either in the chat or Q&A. I know Sharon is managing the Q&A, and I'm also eager to hear from you. So please feel free to contact me, and I'm happy to be in touch with you more about questions you have.
Well, thank you, Claire. That was just fantastic. And I'm a geographer by training, and I learn more every time. And so this is just great. I really appreciate it. One question, and I would just second what you said, that we will have hopefully this item in our auction again next year. So hopefully people will attend the Washington's National Park Fund Spring Dinner and Auction and bid on your hike to the terminus of Emmons Glacier. And if not, you can still go there. So one question I had, Claire, that's been burning in my mind since we did this hike is you were pretty optimistic about the glacier melting. And I've been feeling pretty doom and gloom about climate change and glaciers melting. Where does your optimism come from?
Yeah, I would say it's a relative optimism, but there's been some. I'll stop sharing in just a second, but I'll use this picture to show just to answer that question. So there's a couple of reasons why Mount Rainier might be on a different retreat timescale from other glaciers, even in our state. Number one, the high elevation of Mount Rainier summit means that it's more likely to have some frozen precipitation in the coming years. Even as temperature rises, that high elevation means that we will still receive snow in the coming years. We're also in a maritime climate. And so we expect to still have a delivery of moisture from the Pacific Ocean. While the magnitude of that may change, it won't be so dramatically as to cut off the supply of snow and ice to that high altitude summit. The debris cover to some extent may insulate lower glacier ice from melting, not enough though, but I feel relative optimism given the supply of additional snow and ice, and given the fact that we live in a maritime, a high kind of moisture environment right next to the Pacific Ocean, where Mount Rainier is more likely to receive wet air that can deliver snow, in contrast to, say, for example, a continental location like Glacier National Park.
So you feel more doom and gloom for Glacier National Park then?
Yes, I'm an optimist by training. Can you hear my hesitancy? Not by training, I guess. Actually, not by training. Geologists aren't optimists by training, but I guess by nature I'm an optimist, so it's hard for me. But I think, yeah, Glacier National Park has seen more dramatic retreat and will continue to. And even the Olympics, which are lower elevation, there's some doom and gloom forecasting for that, I think, in the coming decades. So Olympics National Park at a lower elevation will be less likely to receive as much snow as Mount Rainier. Okay,
and Beth asks, does what you say about the maritime climate mean that Emmons Glacier is growing, or is it just not shrinking?
It is retreating, and glaciers on Mount Rainier are in retreat. That is unmistakable. It is the rate of retreat. That's, I guess, a common question that I get is, when are they all going to be gone? And that is likely pretty well into our future that they would be gone. But they're all in retreat. Okay. And so that is it's just the extent to which or how quickly that retreat is happening might be mitigated by more snow deposition at that high altitude sort of catchment area of the summit.
Okay, and related to that, Kimberly asked, how many glaciers are on Mount Rainier?
It depends on who you ask. So that Scott Beeson in 2017, he's the Park Service geologist, published an inventory and lists 29 glaciers and snowfields. That list gets a little shorter if you don't include snow fields. Then a common number you may see cited is 25 or 26. Some glaciers, as they retreat, are separating into smaller ice masses. So we'll see, that number will be an interesting one to follow. And so just sort of check to see what they are counting as a glacier. But a common number that's cited is 25 or 26 glaciers on Mount Rainier.
Okay.
Great question.
That is a good one. And people, please feel free to put your questions in the Q&A or chat. And Kevin asks, have any glaciers on Mount Rainier or anywhere in Washington showed net ice gain over the past decade?
Over the past decade, not to my knowledge, I will say with one exception, and it is an exception in many ways, is that there is a glacier in the summit of Mount St. Helens in the crater. And I believe it has a slightly different trajectory. I don't study that glacier. There are people who do. So there's better information elsewhere. But because it's in a north-facing crater, it does accumulate snow and ice. And there are some, I believe some reports, particularly maybe in the early 2000s, so that's longer than a decade ago, of course, where maybe that glacier was growing. But I haven't looked into that recently. So generally speaking, net ice gain over the past decade is not happening in Washington state.
Okay.
Yeah.
And there's a question, can you tell us what you do on a typical day of fieldwork? So that could be either at Mount Rainier or in Antarctica.
Yeah, so generally speaking, we, whether we're in Antarctica or on Mount Rainier, we're leaving from a camp. And that camp may be a backcountry camp, or maybe in Mount Rainier, maybe a car camping at one of the campgrounds. And we travel for the day prepared for not only our comfort in terms of eating and drinking, but also we have lots of sort of our safety equipment with us. I tell my students our motto is safety, fun, science, that our science is high quality if we feel safe and we feel comfortable and are enjoying ourselves. And generally speaking, we travel. It makes up a lot of our work time. And so often I would say we might be at a field site between 9 and 10, depending on how far we have to go. And then students are working to collect data about the debris cover or about the meltwater stream. And so we typically spend a full day out in the field collecting samples, taking a break for lunch. And those samples may be repeated water samples to get change in time, or it may be traveling through space, so across the glacier, let's say, to get how a feature is changing in space. So there's sampling sites or sampling times kind of drive our rhythm of the day. And then we return, hike back to our camp at the end of the day. So generally speaking, we're in the field all day. Our day is punctuated by these sort of sample collection times, whether rock or water. So.
And Claire, when we were on the mountain, you mentioned in Antarctica having to wait for flights a lot. Can you tell us a little bit more about that? Because that was pretty interesting.
Yeah, maybe. Yes, there's lots of logistical considerations in Antarctica. There are lots of reasons why a plane might not be immediately available to you for good reason. Weather in a continent that is the size of the continental United States, at least, and weather that's not super well known. So that weather can be a reason why you may just have to wait for a while until it's safe, both at your departure point and at your destination point. And also limited resources. The U.S. Antarctic program supports a lot of wonderful science happening in Antarctica. And so it just may be that it's not your turn. So it's a very complex logistical situation getting transported to field sites in Antarctica, and really well supported by the U.S. Antarctic program. They have a tough job. So.
Okay, and Jean asks, maybe we missed this, but what is the methodology for aging moraines, or as my friend and your colleague says, dating rocks?
Dating rocks.
I like to date rocks. So.
Yeah, it's a great question. The study that I cited used dendrochronology. So they are looking at basically counting tree rings or dating. Another way to do it is to do carbon dating of detrital trees. that are entrained in the moraine itself. So that would mean a tree that had died as a result of an advancing glacier, had been deposited by the glacier, and then a radiocarbon date, carbon-14 dating, would say when that tree had stopped exchanging carbon with the atmosphere. So you can use radiocarbon, you can use dendrochronology in terms of tree rings, also sometimes combined with radiocarbon. People use lichens. So lichenometry is talking about how the size of a lichen changes in time. And so if a lichen begins to grow on a glacial deposit, the size of that lichen is giving you an indication about how long that glacial deposit has been there. Some good jokes coming in. And the other thing that people can do to date rocks that I don't have time to give a full explanation of here is that there are nuclides that accumulate in rocks once they are exposed. So it's an atom that's not otherwise found in the rock. And that atom accumulates only when the rock has been exposed to the atmosphere. And so some of the work that I do in Antarctica measures the concentration of those nuclides as and uses that concentration to say, oh, this rock has been exposed for this long. So that's another technique that we use.
Okay, and then in our Q&A box, Chandler asked, the terminus of the Tahoma Glacier is very steep. Any chance there could be a large landslide event, sending large amounts down the creek?
Yes, in a word, yes. So, and there are many. I actually feel relatively safe working in the Emmons Glacier Valley because it's so broad and wide that while I always look up at Little Tahoma and hope it's not the day that it decides to have a rock fall again, it's a relatively wide area. And so rockfall, in terms of the steep valley sides, we hear and you can see, but it's not being delivered to the center of the valley. South Tahoma Glacier, absolutely very steep terrain. It's entirely possible that rocks could be deposited. A big rockfall could happen, and then meltwater could entrain that rockfall and create a debris flow in that way. So there's absolutely landslide-induced debris flow. That's a great question. Yeah.
And if anybody wanted to go check out Emmons Glacier, is it easy to get to? What would you say?
I would ask you, Sharon.
Well, I personally don't know that I could find that. You called it a community trail. There's lots of cairns down the moraine, the lateral moraine, that I don't know that I could find again. But it did seem like you could see your destination. If you look at my image just off in the distance here, it was there.
Yeah.
So I don't know that I think I could do it, but it wouldn't probably be on the right trail.
Yes, we do use a social trail. Some of the Park Service glacier monitoring team, they use the same trail, and we see members of the public on the social trail. So a key to social trail travel in the park, and many of you know this, it's a travel on durable surfaces, which means we are keeping our travel to rocks. And we're not stepping on any sort of fragile meadows or anything. But social trail travel and in the park is possible. And certainly in this context, after we leave the crest of the moraine, we're on a social trail, and there are cairns trying to guide you. As Sharon says, you can sort of see the terminus, like I want to go there. But the cairns help you pick. The only risk would be that you end up in a place where the tree growth is really thick. Or that there's some water from some of the meltwater streams. So the cairns are trying to guide you to the path of least resistance, but even if you missed one, you'd probably still get there. And I noticed the question about miles, that the trail, I would say it's about a mile to the turnoff for Emmons Moraine Trail, maybe another half mile to the moraine crest, where we descend toward the glacier, and then maybe another half or 3/4 mile to the glacier terminus. So I think that's, yeah. So maybe 3 miles-ish to the glacier terminus at most.
Well, it looks like we are out of time, Claire, but this was just fantastic. I learned so much, and as I expected, this was great. And I think your students are really lucky. And like I said, this was a bucket list item I didn't even know was on my bucket list. So so just a reminder that in last year, Washington's National Park Fund raised over $250,000, not miles, to support Mount Rainier, Olympic, and North Cascades National Parks. in these 4 areas. And we thank everybody who's on this call who helps support us. And if you are interested to join us for another virtual field trip, our next one is August 11th to Olympic National Park. It's called Summiting Peaks with the Olympic Mountain Project. And you can join Nate Brown, an adventurer and photographer, to learn about his time spent in the peaks of Olympic National Park. And so I'm going to picture Nate as I'm looking at the Olympics in the future now. But thank you, everyone. And just go to wnpf.org and look for field trips, or feel free to donate. And Kate, Claire, thank you so much for your time. Good luck in your move to your new university. And we really appreciate you. Thank you.
Thank you. Thanks, everyone.
Yeah.